This is the third lesson in our unit on gas chemistry. In this lesson we will focus on the learning targets that are labeled gases 1C and 1B. Define temperature and explain why an absolute temperature scale is necessary, and we want to be able to explain what is known as the gas laws in terms of the kinetic molecular theory. So we'll start with this idea of temperature and what this idea of absolute temperature is. I'd just like you to ask yourself the question, what is temperature? So hopefully you recall from our previous lessons that temperature we define as the average kinetic energy of particles that make up a substance. So another question I want you to consider is it possible for a particle, or anything for that matter, would not have to be an individual particle, to have a negative amount of energy? The answer to that question, of course, is no. Nothing can have a negative amount of energy. The least amount of energy anything can have would be zero. So the question becomes, why do we have negative temperatures then? If temperature is an average kinetic energy and energy cannot be negative, why is it that on the Celsius and Fahrenheit scales, the two scales we're most familiar with, why is it that we have negative values? Or another way to ask it is, what should the lowest possible temperature be? Go ahead and ask yourself that question. Hopefully, when you're thinking about this, your brain's taking you to the realization that if we are actually measuring energy, the lowest possible temperature should be zero. In other words, what we're saying here is the Celsius and Fahrenheit temperature scales, they are not absolute temperature scales. In other words, the zero on either scale does not actually mean zero temperature, because they don't mean zero energy. So we need a temperature scale that actually has a zero value for zero energy. This is what we would call an absolute scale, and we need this if we want to quantitatively assess. In other words, if we want to use a temperature scale that would actually relate to the amount of energy that is in a substance, we need to use an absolute temperature scale. This scale that we use is known as the Kelvin scale. It is an absolute scale. The thing about the Kelvin scale is its size, in other words, going up by 1 Kelvin, is the same as going up by 1 degree Celsius. So the scale itself, the scaling is the same. The only difference is where the 0 point is set. For the Celsius scale, we're familiar with the fact that the 0 point is set at the melting or freezing point of pure water. That's how it was defined. That 0 degrees Celsius was defined as the temperature at which pure water would melt or freeze. For the Kelvin scale, 0 Kelvin is much colder than that. 0 Kelvin is absolute zero. It's the lowest possible temperature. In other words, it's when particles have an average kinetic energy of 0. It's when all molecular motion stops. Those 2 points, 0 degrees Celsius and 0 Kelvin, are off by an additive factor of 273.15. So if you want to convert from degrees Celsius to Kelvin, you will simply add 273.15. Obviously, if you want to go the other way, then from Kelvin to Celsius, you would subtract 273.15. So a good way to help us understand what this whole idea of absolute temperature is to ask yourself this question. What does it actually mean to double the temperature of something? Well, if we're doubling the temperature, what that means is the average kinetic energy of the particles must double. It's not about some number on a scale getting twice as large. It's about the kinetic energy doubling. So here's a question to help us figure out what this all means. We're told a gas is at a temperature of 10.00 degrees Celsius. The temperature is doubled. What is its new temperature in degrees Celsius? The first thing we want to get out of the way here, as far as what this answer is not, it is not 20.00 degrees Celsius. Yes, we certainly know that the number 10 times 2 is 20, but going from 10 degrees Celsius to 20 degrees Celsius, we have not doubled the kinetic energy of the particles. The only way we can do this is to look at the Kelvin scale, because on the Kelvin scale, those values are proportional to the kinetic energies of the particles. So the first thing we would need to do is convert our temperature of degrees Celsius into Kelvin. So 10 degrees Celsius, I add 273.15 to that. That's going to give me 283.15 Kelvin. That is the temperature scale that gets doubled. So I take 2 times 283.15, and that's going to give me a temperature of 566.30 Kelvin. And if we want it in Celsius, we would then subtract our 273.15 to get 293.15 degrees Celsius. So we start at a temperature of 10 degrees Celsius. If we want to double the temperature, we'd have to take it to 293.15 degrees Celsius. Hopefully this gives you an idea of what we mean by an absolute temperature scale, what we mean by being able to double the temperature or triple the temperature or cut it in half, any of those things. We have to use the Kelvin scale. Alright, so this leads us into looking at the gas laws, and we will continue to use this idea of absolute temperature whenever we get to the gas laws that involve temperature. So here's a scenario I want you to consider, just a picture to start with. We have a gas in some sort of container. You'll notice here the schematic shows you 5 particles of gas. The volume in that container is then reduced. We have some sort of piston here that is compressing, and so it's cutting the volume down. So my question is this. So we have the volume of a fixed amount of gas is reduced while its temperature is kept constant. So we're holding this gas at constant temperature in some manner. And the question is, what will happen to the pressure exerted by the gas? Use the kinetic molecular theory to explain. So pause the video, take a second, ask yourself, what's going to happen to the pressure exerted by the gas as this volume is decreased, and use our ideas of the kinetic molecular theory to explain your answer. Alright, so recall that gases will always exert pressure due to the collisions between the particles that make them up and the container. So ultimately, whatever changes in the pressure occur due to changes with the collisions that occur between particles and the container. So if we reduce the volume that the gas occupies, that will reduce the space for the particles to move. There's less room. This causes the particles to collide with the container more frequently. They're just going to hit the container more often. So ask yourself, what's going to happen if they collide with the container more often? What will happen to the pressure? Well, the answer is it's going to go up. In conclusion, reducing the volume of a fixed amount of gas at constant temperature will increase the pressure it exerts. As we continue to reduce the volume, the pressure will continue to increase. Now we can get more specific with this scenario. We can put some numbers with it. So let's say here we cut the volume in half. So notice we're going from a volume of 1 liter, V1 is 1.0 liters, to a volume of half a liter, V2 equals 0.5 liters. Our initial pressure here before we reduce the volume is 100 millimeters of mercury. I want to know what our new pressure is going to be over here. So more specifically, what will happen to the pressure of the gas if the volume is cut in half? Again, use your kinetic molecular theory to explain. So if the volume is cut in half, the number of collisions between the gas particles in the container, that's going to double. Because there's half the space, they're going to collide twice as often. So if we have twice the number of collisions, that will double the pressure. So whatever pressure we had, in this case 100 millimeters of mercury, it's going to double, multiply it by 2, it'll be 200 millimeters of mercury over here. So this leads us to this statement about the relationship between pressure and volume. The pressure of a fixed amount of gas, and we'll talk about that in a second, what that means. The pressure of a fixed amount of gas is inversely proportional to its volume at a constant temperature. So the key idea with this fixed amount of gas is we have the same amount of stuff. We're not adding any particles, we're not removing any particles. In other words, it's a closed container. There's no gas going in or out. So if we have the same amount of gas, and if we hold it at constant temperature, the pressure and volume are inversely proportional to each other. Another way we could write that mathematically would be in this manner, where we have our symbol for pressure P. This symbol here is the Greek letter alpha. That means proportional. Anytime you see that in an equation, actually this isn't an equation, it's not an equal sign, but anytime you see that alpha symbol, that means proportional to. And then it's inversely proportional because it's 1 over, you can see our notation here, 1 over V, the volume. So pressure is inversely proportional to volume. So what that means more precisely, in case we're unsure what this whole inversely proportional means, is that when one variable is inversely proportional to another, what this tells us is that the factors of change for the two variables are inverses of one another. So for example, if the variables a and b are inversely proportional, if a's factor of change is 2.7, meaning I multiply a by 2.7, then b's factor of change will be the inverse of that, 1 over 2.7, or in other words, it would be divided by 2.7. That's what inversely proportional means. So notice in this example, our volume is cut in half. Our volume's factor of change is 1/2. I multiply it by 1/2. So our pressure's factor of change is the inverse of that. Well, the inverse of 1/2 is 2. So I'd multiply it by 2, and the pressure over here would be 200 millimeters of mercury. This relationship here is known as Boyle's law. Now, I am not concerned that you memorize the names of these relationships. I put these on the presentation just because the more you study this stuff, or if you're taking another class sometime, you will see this referred to as Boyle's law. And all of these gas laws have a name with them. I'll give them to you. Again, you don't need to worry about memorizing which name goes with which relationship. What we are much more concerned with is we want to make sure we understand this. Pressure is inversely proportional to volume, and we will get all sorts of practice with that. All right. Let's look at a different relationship here. So now notice we have a gas, and it's in a closed container. In other words, no gas going in or out. So again, we have a fixed amount of gas. The volume of the container is held constant this time. Okay, so we're not changing the volume, but what is happening is we're increasing the temperature. Notice we have a little Bunsen burner here, so we're heating up the gas. We have a gas at some temperature over here. We measure its pressure, then we heat up the gas, and the pressure would change. Okay, so we have the temperature of a fixed amount of gas is increased while its volume is kept constant. My question is, what will happen to the pressure exerted by the gas? Use the kinetic molecular theory to explain. So as the temperature is increased, the gas is going to exert more pressure. This is because as the temperature goes up, the particles that make up the gas will move faster, at least on average. Some of them won't move any faster, but on average they will all move faster. This increased velocity, it really results in two things. A, we're going to get more collisions. They're traveling faster, so they're going to collide with the container more often. But also, and this is really the more important factor, because those particles are traveling faster, each collision will apply more force. So this increased number of collisions and the increased violence of the collisions will exert more pressure on the container. So in summary here, increasing the temperature of a fixed amount of gas, if we keep the volume constant, that will increase the pressure that the gas exerts. So like before, let's get a little more specific with this and put some numbers on it. So notice here for the first scenario, we have an initial temperature T1 labeled at 200 Kelvin, and recall the importance of using the Kelvin scale in these problems. We increase the temperature and we've doubled it to 400 Kelvin. So recall, if we're talking about the Kelvin scale, we actually have doubled the temperature, meaning we've doubled the kinetic energy of the particles that make up this substance. So if our initial pressure is 1.5 atmospheres, I want to know what the pressure is once we've doubled the temperature. So what will happen to the pressure of the gas if its temperature is doubled at constant volume? Again, try to use your kinetic molecular theory to explain. So doubling the temperature of the gas will double the average kinetic energy of the particles. We kind of already have that idea from our discussion on temperature. So doubling the kinetic energy of the particles, that will double the pressure exerted by the gas, just because there's twice as much energy there. So our relationship here is the pressure of a fixed amount of gas is directly proportional, no longer inversely, directly proportional to its temperature when held to a constant volume. The notation we can use for that, you can see here, pressure, and then we have that alpha sign, again that means proportional to, and if it's not 1 over, then it's directly proportional. So pressure is directly proportional to temperature. Now what directly proportional means, should be fairly straightforward, is that the factors of change are the same. So in other words, if A and B, if those variables are directly proportional, and A's factor of change is 2.7, so say I multiply A by 2.7, then B's factor of change will also be 2.7. In other words, it's also multiplied by 2.7. So here our factor of change is 2. The temperature was multiplied by 2 to go from 200 Kelvin to 400 Kelvin. So my pressure will also multiply by 2, going from 1.5 atmospheres to 3 atmospheres. This relationship here between pressure and temperature is known as gay-Lussac's law. Again, don't need to worry about the names. Just want to throw it out there so you are familiar with it if you ever see it sometime else. All right. So if you think about these relationships, we've looked at the relationship between pressure and volume. We've looked at the relationship between pressure and temperature. There is one other possibility. And you're probably thinking, well, that's between temperature and volume, and you would be correct. So here's our scenario. So we have a balloon containing a gas, obviously. And the reason a balloon is good here is because if you think about this relationship, if we're studying the relationship between temperature and volume, then what we're holding constant here is pressure. And the thing about a balloon is, as long as it's just a normal everyday balloon, the volume of that balloon will always adjust so that the pressure of the gas inside equals the pressure of the gas outside. It will equal atmospheric pressure, in other words. So this tells us that the gas in the balloon is going to maintain a constant pressure. If we have a balloon that can just expand and contract like any regular balloon. So in this scenario, we have a balloon that contains a gas, and then we're going to heat it up. We're going to heat up that balloon. Obviously, if the balloon could pop and whatnot if we're actually heating it with a Bunsen burner, but we're just going to ignore that fact. So we heat up the gas in the balloon. So my question is this. The temperature of a fixed amount of gas is increased while its pressure is held constant. So what will happen to the volume occupied by the gas? Use the kinetic molecular theory to explain. Alright, hopefully in some ways, even though we're told we're keeping pressure constant, you're thinking about pressure. Because remember, if the volume of that balloon were to stay constant, the pressure would have to go up because those particles are going to be moving faster. So ask yourself, what would have to happen to the volume of that gas? What would have to happen to the volume of the balloon to keep the pressure from going up? So increasing the temperature would increase the pressure if the volume was constant. In other words, if this balloon did not change its volume, that pressure will go up. This would be due to the increase in the number and the violence of the collisions between the particles and the balloon. The only way that the pressure would stay the same, to be held constant, would be to reduce the number of collisions. This will only occur if we give the gas more space. So in other words, the volume of the balloon must increase as we heat it up if the pressure is to stay the same. So in conclusion, increasing the temperature of a fixed amount of gas at constant pressure will increase the volume it occupies. So just like our previous relationships, we are going to put some numbers on this. So let's say we have this scenario where the temperature of the gas in the balloon to start with is 200 Kelvin. Again, remember the importance of the Kelvin scale. And we are going to double it to 400 Kelvin. So we have doubled the kinetic energy of the particles in the balloon. I want to know what happens to the volume to keep that pressure the same. So what will happen to the volume of the gas if its temperature is doubled under constant pressure? Use the kinetic molecular theory to explain. As we discussed previously, in order to keep the pressure constant, the volume must change in such a way as to counteract the temperature change. Since the temperature of the gas is doubling, the volume will also need to double. In other words, we need to give the particles twice as much volume to move if we want to keep the pressure constant. So the relationship here is that the volume of a fixed amount of gas is directly proportional to its temperature when held to a constant pressure. The mathematical expression for this, you can see, is V is proportional to T, again, for constant pressure. And we already discussed what directly proportional means. Again, that means the factor of change is the same. So if we double the temperature as we did here from 200 to 400 Kelvin, our volume will also double from 1 liter to 2 liters. This relationship here is known as Charles' law. So one last slide here to summarize these gas laws and to put a little more thinking into these relationships. So for a fixed amount of gas, and remember all of these are for a fixed amount of gas. We're not adding any gas to the container, removing any gas, it is closed. So we have the same amount of gas the whole time. For a fixed amount of gas, we have learned that volume is inversely proportional to pressure, and that's whenever we have constant temperature, and that is known as Boyle's law. Once again, don't worry about memorizing which names go with which relationships. That's really not important. We have learned that temperature is directly proportional to pressure if we have constant volume. That is known as gay-Lussac's law. And finally, we have temperature is directly proportional to volume whenever we have constant pressure. This is known as Charles' law. An easy way to remember this, or at least it is for me, what I always used, I just remember that if I'm talking about temperature and its relationship to the other two variables, it's always directly proportional. Temperature is directly proportional to pressure. Temperature is directly proportional to volume. If it doesn't include temperature, notice here this first one, we're talking about the relationship between volume and pressure, that's when it's inversely proportional. So if you're looking for a way to help you remember this, temperature directly proportional all the time. If it doesn't include temperature, inversely proportional. So let's put these ideas in perspective here. I'm going to ask you just, I think it's 3 questions here about these relationships. And here's how the question goes. For each scenario, determine the factor of change for the pressure a fixed amount of gas would experience in each. So when we say determine the factor of change, we're essentially meaning what are we going to multiply it by? Are we going to multiply it by 2, meaning it doubles? Are we going to multiply it by 1/3, meaning we divide it by 3, so it's cut by 1/3? What are we going to do in each scenario? So here's the first one. The volume is tripled at constant temperature. So what you want to do is you want to think about these relationships here and ask yourself which one applies. Well, we have constant temperature here, so we're talking about this Boyle's law relationship. The volume is inversely proportional to pressure. So the volume is tripled. So we've multiplied the volume by 3. Ask yourself, based on that relationship, what's going to happen to the pressure? What would we need to multiply it by to figure out its new value? So if volume and pressure are inversely proportional, as we have learned, if we multiply the volume by 3, the pressure must be multiplied by 1/3. In other words, divided by 3. So whatever the pressure was to start with, we would divide it by 3 as the volume is tripled. So just ask yourself, does this make sense? If the gas volume is getting larger, it's occupying more space, that's going to reduce the number of collisions, and that should decrease the pressure. In fact, it'll decrease the pressure by a factor of 3. All right, next one. The temperature is cut in half at constant volume. So this one, we're asked about the relationship between temperature and pressure. So ask yourself, what's the relationship between those? Well, temperature and pressure are directly proportional. So if we cut the temperature in half, that means we've multiplied it by 1/2 or divided by 2, however you want to think about it. And if temperature is directly proportional to pressure, then the pressure must also be multiplied by 1/2. So its factor of change would be 1/2. And I have one more for you here. So this last one here, it's actually, we're making 2 changes simultaneously. We're told that the temperature is tripled and the volume is doubled. So you might be wondering, well, how will I know what's going to happen to the pressure if both things are changing? Well, it doesn't matter that both are changing. We can still consider each one individually as if the other was held constant, and then we can just put those changes together. So if the temperature is tripled, that means we're multiplying it by 3. And if the volume is doubled, that means we're multiplying it by 2. So just consider each one individually. If we were to multiply our temperature by 3, what would happen to the pressure? Well, if you think about temperature and pressure, those are directly proportional. So if we multiply the temperature by 3, the pressure should also be multiplied by 3. Now let's consider the volume change. If we multiply the volume by 2, knowing that volume and pressure are inversely proportional, our pressure would be 1/2 of what it was. The factor of change would be 1/2. So each individually we know, but we actually do both of these at the same time. We triple the temperature and we double the volume, so the factor of change for the pressure will just be the product of these two. It would be the product of 3 and 1/2, so 3 times 1/2 is 3/2. So the pressure is going to be 1.5 times larger than what it was to start with. So in this lesson, we have looked at the learning targets 1C and 1B. We defined temperature and we explained why an absolute temperature scale is necessary. We also looked at the gas laws and explained them in terms of the kinetic molecular theory. We'll have one more lesson in this first series of lessons for this first learning target, and that will explain this last point here, the conditions under which a gas would behave most ideally.